With? Oh, that's principal stresses is deform. Okay, we'll talk about that later. Yeah. Yeah. Any other questions? Yeah. Okay. We might be able to do it right after class. Okay. Okay. So last time we were talking about centroids. And I wanted to just say one more quick thing about it. So the centroids, you can think of it as the position vector of the centroid. So that's why I'm writing this as a P. Is 1 over the total area. This is for 2D. Times the sum from 1 to n of the area of the ith piece times the position vector of the ith centroid. Okay, it's just a little bit different notation, but it's the same thing we were talking about last time. But if you think about it with this notation, you can take the time derivatives of both sides. And it gives you a sum formula that's sometimes useful for the velocity of the centroid and the acceleration of the centroid. So the velocity of the centroid is equal to 1 over the total area times the sum of the ith area times the velocity of the ith centroid. And the acceleration of the centroid is 1 over the total area times the sum of the ith area times the acceleration of the ith centroid. These both work for 3D also if you replace the areas with volumes. There aren't too many times that you need to know the velocity of the centroid of some complicated shape. This one comes up a lot because the acceleration of the centroid, usually in most cases, if you're dealing with homogeneous things and uniform thickness, the acceleration of the centroid is the acceleration of the center of mass, and the acceleration of the center of mass is what comes up in Newton's second law. So this is a really useful formula. Not on the FE exam. Fundamentals of engineering, I think people usually take it as juniors or something like, yeah, it's kind of like just a SAT type test of your knowledge of the fundamental engineering classes. Nope.
If you want to get a good paying job, just like if you don't know what you're doing, then yeah, don't take it. Because that'll be I feel like, oh, Nick's a retard. He took that FE exam and failed 3 times.
Can we go back to dynamics now? How about we'll spend the next 45 minutes doing dynamics, and then you have the next 47 hours to discuss the FE exam. How many hours you have?
Yeah.
Okay, so we just talked about centroids. What are we doing this for? So we are in the middle of, so we're talking about rigid body kinetics. And in order to do rigid body kinetics, there were 3 things that we had to define. Center of mass, which I mostly talked about just as a calculation of centroids. In all the cases that we're going to consider, they are the same thing. Done with that. And so now we need to introduce 2 other things. The first one is mass, moment of inertia, a point. That's a super long thing to say, so people just call it moment of inertia. But you need to keep this in mind, the whole long thing in mind, because there is also a there's also a moment of inertia. You call it the moment of inertia. You use the same notation for it. The calculation is similar that you use in deform, but they're totally different things. And so in those 2 classes, I'm going to try to be real clear about, what each one does. And then the third thing we have to talk about is the moment of force of point. And that people just call the moment. But again, you got to keep that other stuff in mind. Okay, so now we're on the mass moment of inertia about a point. And you can think of this as just the rotational version of mass. So like, similarly to how mass measures an object's resistance to acceleration. The mass moment of inertia about a point. Mass moment of inertia. Measures an object's resistance to angular acceleration. Bless you. So like, I wish I could draw a figure skating one since it's Winter Olympics right now, but I'm going to draw this gymnastics picture. So if, what? They don't do this in skating unless things are going really wrong. Actually, people can do it, and it's illegal in the Olympics. Yeah, they can do one flip. Okay, so let's say your coach you can't do doubles and stuff. Not allowed to, because it's dangerous, I guess. No, you're not allowed to. Yeah. Okay, so if your gymnastics coach is like, yo, go do a double flip. And, there are two ways to do it. There's more than two, but these are two. No, draw it. You can draw it.
How much practice you need to go there?
I've drawn this every semester, so. Okay, so. So this is layout position and this is tuck position. And if your coach doesn't specify you want to do the tuck position, okay, this layout position is hard to get rotating. And so this is a high moment of inertia. Really, I guess you would say causation goes the other way. It has a high moment of inertia, and that's why it's hard to do this. It's hard to get, you can't get it rotating as fast because it's hard to accelerate, and therefore you got to get a lot higher to make a double work. The moment of inertia is denoted with a capital I sub A. This is easy to get rotating. And so this is a low mass moment of inertia. The integral definition for moment of inertia. That is the point. So mass moment of inertia about the point A. So the integral definition says I sub A is equal to the integral over the entire area of R squared dm. And now that I think about it, that should not be the area, that should be the mass. Okay. Where R is the distance from the point A to the little bit of material dm, that small increment of mass, and m is the total mass. And just like with the centroids, we're not going to use this integral formula. We're going to use formulas that people have derived using the integral formula for different shapes. One thing to notice here is I sub A is different for different choices of A. And this A you can think of, I always call it the about point. But since we're only going to use the mass moment of inertia about a point for the moment equation, if you remember, I said that the moment equation is only valid for two choices of about point. That's if you happen to have a fixed point on the body, Otherwise, it has to be the center of mass of the body. So so you can calculate the mass moment of inertia for any point you want. You know, it makes sense as a mathematical thing. But if you're going to use it in the moment equation, there's only two cases that you would look for. Okay, so let's think about what it means and make sense out of it with these two pictures of doing gymnastics practice. Good job, Jay. Okay, so what this says is, so break up the body into a bunch of infinitesimal points, dm, and calculate the integral of all that mass times the distance squared. You can just think of that as like the distance, intuitively. So you're going to get a big value of this. Okay, let's say that we have the same total mass, okay? 50 kilograms or 100 kilograms or whatever, same mass. And so how would you get this value big without changing the mass? You would spread that mass as far away from the point A as possible. So if the point A is the center of mass, what this says is if you take your 100 kilograms and spread it out into a thin ring around that about point, you'll have a way higher mass moment of inertia than if you squeeze all that mass to right around the point A, okay? Because you're getting value for all that distance you move the mass out. Okay, so that's why this has a higher mass moment of inertia than that. In this case, what the person's trying to do is get all of their mass concentrated as close as possible to the center of mass. In this case, there's a lot of mass all the way this distance away from the center of mass, somewhere like belly button or something, and legs are spread out. And so even though it's the same amount of mass, it's spread away from the center of mass. Yes?
What distance would you like dividing up?
Well, if they're infinitesimal, then there's only one point,
Oh.
But, so to do that calculation, you would separate this up into like concentric rings where everything on your ring is some fixed distance from.
So if we were to put that in a three-dimensional coordinate system, and they're rotating about the z-axis, the reason, or the one that is completely stretched out, is going to be harder for it to start precession than the one on the right?
It's going to be harder to get. So he starts out with 0 angular velocity, and he's trying to very quickly get up to a high angular velocity. That's a lot of angular acceleration. And so it's a lot easier to do with that than it is with that.
But that will keep its speed for longer than the one on the right.
Yes, that is correct. Yep. Okay, so let me just give you the formulas. So I'm going to give you formulas for the moment of inertia for 4 common shapes. Where do you hit the ground? The ground is pretty good at stopping angular velocity. Okay, so first is a slender rod. Yes.
Just going to see that once it's faded up.
That's right. Yep. Okay, so call this X, this y, and this z. And notice that with a shape like this, I mean, in general, any shape, the body doesn't, even once you choose the about point, a three-dimensional body rotates more and less easily about axes in different directions. So if you think about rotating this thing around the y-axis, everything's squeezed pretty tightly to the x-axis, right? If you're talking about rotating it just like a barrel roll, everything is squeezed pretty tight, so that should be a small mass moment of inertia. In fact, in this case, we're assuming that it has no thickness, so really that would be 0, but you'd never model something that way if you were talking about a rotation about x. But then to rotate about y or about z, then you have that thing tumbling, okay? And that's going to be a lot harder to get rotating. So I have to give 3 separate formulas. So first, the mass moment of inertia about the x is 0. You would never use this, you know. Something with 0 mass moment of inertia gets spinning with an angular acceleration of infinity with 0 moment. It doesn't make any sense. The 2 you would use are rotations about the y and rotations about the z, and those are both the same. And those are 1/12 times the mass times the length squared. So this is the length is what you would think it would be. Yep. Yes. Second one is a thin rectangular plate. And so when I say slender or thin, I mean we're assuming that the thickness is 0, or and because of that distance squared thing, things don't actually have to be that thin for the thickness to have basically 0 effect on it. If you think about something as having a thickness of like a tenth of, well, yes, let's say a tenth of whatever unit you're using. Well, then you square that distance and it becomes 100th, you know? So that square in the distance means that this slender approximation works really well for a lot of things. Okay, thin rectangular plate. So it's good exercise. That was even worse. I'm just going to draw this the rest of the time. Okay. And the axes, call that z-axis. X-axis is this way, and y-axis is this way. And the dimensions, I'll call this B. This is C, and the about point is the center of this shape. The about point was the center over here, too. Okay, so the mass moment of inertia about the x-axis is 1/12 times the mass times b squared plus c squared. Notice that if one of those, like, say this little one reduces down to 0, this equation reduces to the equation for the slender rod. Rotating about the y-axis, what matters is that length c, so this just is 1/12 times the mass times c squared. And about the z-axis, what matters is that length b, so this is 1/12 times the mass times v squared. Yeah. So you have to differentiate on these between whether the thing is rotating like a blade or like a paddle. Those are the best words I can come up with. But you know, this is like about x is like and about y or about z are rotating like paddle wheels. You can watch the video. So this is like a blade. And these two are like paddles. I guess so, yeah. Yeah, like a ninja star. And that's going to be an important thing and sort of a confusing thing sometimes. You're going to have to figure out which of these cases you're dealing with. You know, you'll just see the shape and the motion and whatever, and you'll have to figure out which of these kinds of rotation you're dealing with. We are not. But when you have to do that, the mass moment of inertia is a matrix, not a number. We're only going to do two-dimensional. In the past, I used to do a little bit of three-dimensional, but I'm replacing it with something else this semester. But there's some problems there if you want to look at what kind of problems, you know, that comes up in.
Are they harder problems?
They're hard, yeah, and it's no, they're hard. I mean, that was the hardest topic in the class, and I don't think it was worth the amount of time that it took. So we're going to do something else that'll come up more often. Number 3 is a thin disk. The about point is the center. The one going out of the front of that disk, the direction it would roll, is x. The one going to the left is z, not y. And the one going up is y. And again, on this one, you have to think about, is this rotating like a blade or a paddle? What's the axis of rotation that makes it a blade? V, yep. Yeah, that was part of my engineering training. Yeah. 46 newtons of force at precisely this location. Yeah.
While the wheel's spinning.
Yeah, exactly. Blindfolded. So mass times the radius squared. The radius is the radius of the disk. And then Ix and Iy are both the same. That is, no, that's a good question. I forgot something important. Over 2. Oh, yeah. I got distracted. Who asked me that question about throwing stars? And then the other 2 are half as big. So mr squared over 4. This one is the blade, or rolling like a wheel. And these 2 are the paddle. And it's actually easier to get it rotating in the paddle orientation than in the blade orientation. If that goes against your intuition, you're probably thinking of air resistance, you know. But and then the last one is a sphere. Because of air resistance. Yeah. Yeah. Okay, so there's X, Z, Y. And as you would expect, all 3 of these are the same. Ix is equal to Iy is equal to Iz. And it is 2/5 mr squared. So if you have a disk and a sphere and they both have the same mass, it's easier to get the sphere rotating than the disk. Yes, that's all I'll say right now. Peter will do a thing, and maybe you've done this in physics briefly, but we'll think about a lot of different shapes and calculate which ones would roll down a hill fastest. Would, you know, like if you raced a disk in a sphere and a hollow ring down a hill, which one would win? Well, the smaller the mass moment of inertia is, the faster it's going to, you know, spin up. And so a sphere is going to beat a disk down the hill, which is going to beat a ring down the hill. Okay, so one thing to notice here is these formulas only work for a single about point. So these are only valid for the about at the center. We need new formulas anytime we want to rotate one of these about a different point. You know, like what if there was a fixed point that wasn't at the center? Would we need a formula we don't have? So do we need new formulas for each about point we use? That would be bad, but it turns out we don't. Yes, exactly. because of parallel axis theorem. Oh yeah, really? Everybody's always trying to squeeze the rotational, the rigid body stuff in at the end of physics 1. Okay, so parallel axis theorem says if you have some arbitrary object, and this is the center of mass, and you have an axis C that goes through the center of mass. And then you have a parallel axis that goes through this point A. So these have to be parallel. Then the mass moment of inertia about A is equal to the mass moment of inertia about the center of mass plus mv squared. Where d is this distance. Okay. Notice that that says that the smallest moment of inertia an object can have is one that goes through its center of mass, because md squared can't ever be negative. I am not doing that exactly. We are not. Yes. That's true. Okay, so say we have this rectangle. This length is 1 meter. This is 2 meters. And we want to calculate the moment of inertia about A. Oh, let's give it a mass too. Say the mass is 10 kilograms. So what's I sub A? So first, the mass moment of inertia about the center of mass is 1/12. Are we talking about this rotating like a blade or a paddle? That's true, but I drew it in a 2. So anytime you see it in 2D, you can imagine that it's thin going into the page. And so we have to take both of these two distances into account. And so this is going to be 1/12 times 10 times the quantity 2 squared plus 1 squared. That is 5/50/12, which is 4 1/6. which is 4.16 repeating, kilogram meter squared. And now, what's the distance from the center of mass to A? We can use the Pythagorean theorem. Well, distance squared is equal to 0.5 squared, because you're going half of that horizontal distance, plus 1 squared, so 1.25. Yeah, but we want distance squared. I just for the parallel axis theorem, so we just square it again at the end anyways. Okay, so the mass moment of inertia about A is equal to mass moment of inertia about the center of mass plus the mass times the distance squared. So that's 4.16 repeating plus 12.5. And that's 16.6 repeating kilogram meter squared. That parallel axis theorem contribution, notice how big that was, you know. If you think of this as like sort of the contribution of the shape itself, the contribution of the parallel axis theorem was a lot bigger than the contribution of the shape itself. And that's true a lot of times, especially in engineering applications, if you're trying to have a big mass moment of inertia, the shape, the effect of the shape is going to be, you know, insignificant compared to the benefit of getting that mass far away from whatever you're rotating around. Okay, and I mentioned this before, but notice this moment of inertia I sub A is not the same as the moment of inertia IA, if you can believe it. You call them the same thing. The notation is exactly the same, but that comes up in D form. So don't get confused about those. The one that we use in D form is no, IA and D form. Yes, that's for sure. That's 100%. Put all your money in Vegas on that one. Damn it! Find out if they have a bet on the different cylinders rolling down the hill. That sounds like a Sesame Street skit. Hey, buddy, come in here. Which of these cylinders do you think will roll faster? The guy with the watches inside his jacket. Yeah, hopefully. All engineers and scientists yeah. We've got to win this time. We've lost 100 times in a row. Okay, so the one in D form is called the area moment of inertia, not the mass moment of inertia. about a point. And instead of measuring the resistance to acceleration, angular acceleration, it's a measure of a cross-sections, so a cross-sectional shape, cross-sections resistance to bending. Any questions about that? Okay, so we're doing rigid body kinetics. And so now we've defined the center of mass. And we've defined the mass moment of inertia about a point. And so the last thing we have to talk about is the moment, or the moment of a force about a point. So we'll do that next time. Any questions? No. We can. That would probably come up in an intermediate dynamics class or even advanced dynamics. The intermediate dynamics would be something you would take, I guess, as a junior or senior. And it would probably, if you're mechanical engineering, it would be an elective. If you're aerospace, it would be required probably. Yes?